Welcome to the part 2 of our Frontier webinar series. Today we're going to take a look at some in-depth applications on the PYGCMS side of things. But first, let's take a look at our agenda. We're going to start off today with a brief recap of what happened during our previous webinar. We're going to cover things like where can you use pyrolysis GCMS as a technique. At that point, we will then transition into our applications, which cover a variety of fields, such as microplastics, phthalate esters, forensics, commercial products, and even material testing in the PYGCMS applications. If you have any questions throughout this webinar, please feel free to submit those, and we will make sure to get to those questions as we can. Without further ado, let's begin. If you joined us for our first webinar, then this slide would look very familiar to you. If not, then no problem, but I would highly suggest you watch the on-demand version as there is some very useful information on the fundamentals of pyrolysis. Kind of like this slide. Where can you use pyrolysis? Well, the short answer, there is no short answer. Pyrolysis in today's world incorporates much more than just the analysis of polymers. Due to the versatility of this technique, areas of interest such as contamination, comparison, quality control, and unknown analyses can be delved into. Pyrolysis is also extremely useful in material characterization. For example, additives, plasticizers, surfactants, volatiles, films, impurities can all be analyzed from a mixture of polymeric samples in many different industries, such as paint, coating, petroleum, plastics, elastomers, microplastics, and consumer products, and that's just to name a few. Today we are going to cover just a few of these, but in greater detail. Each of these applications are increasing in popularity, but unique in their own way. It is important to note that each application that we discuss today will be available for download in the additional resources section. First up, we have microplastics. Now, the image we see here is not truly the best depiction of microplastics. Granted, this is a giant trash heap of plastics, but it doesn't necessarily constitute what we see as a microplastic. This then begs the question, what is a microplastic? Why are we so concerned about them? And how does this even relate to pyrolysis at all? Well, if you're one of the viewers asking these questions, then get ready for your answers. So, what are microplastics? Well, simply put, they are very small pieces of plastic, but more specifically, any plastic that was within a 5 millimeter down to several micrometer size range can be labeled as a microplastic. Now, there are two categories of microplastics, primary and secondary. Primary microplastics would include plastics already within that size range before being introduced to the environment. This would include things like microfibers from clothing, nurdles, or plastic pellets, as well as microbeads, which are often found in things like cleaners and even cosmetics. Secondary microplastics are the result of degradation of much larger plastic products, similar to the image of what we saw on the previous slide. Microplastics have become a huge environmental concern due to their impact on natural ecosystems, their presence more heavily felt in marine ecosystems. The biggest concern with microplastics is the length of time that it takes to fully degrade, taking upwards of hundreds or even thousands of years. It has been pointed out that certain things like bioaccumulation may also occur by a process of adsorption of harmful substances onto the microplastics, and then ingestion of those microplastics by either marine organisms or humans may cause problems. Due to that, many surveys of the actual condition of microplastics and evaluation of their toxicity are continuously being conducted. So how do we go about testing for microplastics? Well, when it comes to analytical instrumentation, the FTIR can be used for the qualitative analysis of comparatively large microplastics. Now, on the other hand, the FTIR microscope employs an infrared microscope, and this is mainly used for fine microplastics that cannot be analyzed by the ATR method of FTIR. The FTIR microscope enables highly sensitive analysis of those finer microplastics with a size of approximately 10 micrometers. However, there are certain cases where it is difficult to distinguish the microplastics that contain multiple types of these fine plastic particles. In this case, We can see where pyrolysis, gas chromatography mass spectrometry, or PYGCMS, can be a very effective method for microplastic characterization and identification. Of the day. In this application, we will cover the experimental methods of the analysis of microplastics by PYGCMS. Starting with the sample prep, approximately 0.05 milligrams of the 4 types of commercially available standard polymer samples like polyethylene, polypropylene, polystyrene, and polyvinyl chloride fragments were all weighed and placed into the same sample cup. And about 1 milligram of wool was placed over top to prevent scattering during sampling. Now, in order to identify the presence of microplastics, single-shot pyrolysis was used here at 600 degrees C. The MS was set to a scan range of 29 to 700 mO/Z. But we were also simultaneously simming the pyrolysis products shown in the table. The pyrolysis products for PE, polypropylene, polystyrene, and PVC. By monitoring these ions of the pyrolysis products, we were able to perform qualitative analysis with highly sensitive detection. The chromatogram shown here shows the total ion current chromatogram, or the TIC chromatogram, obtained by analyzing the mixed sample containing multiple polymers. Since the result of this analysis takes the form of a complex chromatogram in which the pyrolysis products of these respective polymers are intermixed, at this point it is somewhat difficult to specify the individual polymers contained within the sample from this chromatogram alone. However, if we take a look at the SIM chromatograms, we can positively identify the presence of the pyrolysis products for the respective polymers, as shown in the figure on this slide. By tracing these specific pyrolysis products in the polymers, the contents of the polymers could be specified more accurately. Even multiple polymers were intermixed in a sample, thus proving PYGCMS is an effective method for identifying and characterizing microplastics, or polymers, or pyrolysis products within microplastics. Innocent child's toy or hazardous substance carrier? Possibly both? Well, this has nothing to do with the possible germs on the toy, but more so its composition. See, toys like this are filled with things like plasticizers that affect the toy's physical properties. What we will discover in this next application is that children's toys are not the only culprit for hazardous substances. This brings us to our next application, phthalates, or phthalate esters. These esters of phthalic acid are commonly used in plasticizers, and rightfully so, as we can see the many benefits, like increased flexibility, as well as transparency, even prolonged durability and longevity. Unfortunately, the side effects are much worse than the benefits. Phthalates are what we know as endocrine disruptors, where they enter the bloodstream and disrupt sex hormone production in infants and adults alike. Now, this becomes an even bigger concern when we take a look at just all the things phthalates are used in. For example, there's medical devices, detergents, surfactants, packaging, and children's toys. And all of these are just what's universally found in PVC, not to mention all of the other plastics out there. If these substances are so toxic, who or what regulates them? Well, RoHS compliance does just that. The restriction of hazardous substances impacts the entire electronic industries. This organization created the original directive, which was adopted all the way back in February 2002 by the European Union, but it wasn't until 2006 that the first restriction of substances was actually released, which included 6 substances. Part 2 of RoHS compliance was to ensure that CE marking or compliance marking on all products that were compliant. It also requires periodic reevaluations that facilitate gradual broadening of its requirements to cover additional electronic and electrical equipment, things like cables and spare parts. This directive took place in about 2011. And finally, in the third and final RoHS directive at this point, 4 new components were added to the list. And yep, you guessed it, phthalates. In this development, the IEC worked to establish a method where the 4 phthalate esters could be tested and make sure that the limits were below a 1,000 ppm level. So how do we test for phthalates at a 1,000 ppm level? Well, the traditional method, or the determination method, required some form of solvent extraction paired with GCMS. Now, there were plenty of downfalls and plights with this, including large cost in solvent use, as well as the disposal of said solvents. This method also led to lengthy analysis times, which limited the number of sample throughput. And finally, there was often difficulty in extracting phthalates with similar functional groups, which led to some pretty inconsistent recoveries. Now, in the newer school method of screening/semi-quant method, we can use PY GCMS. Now, what are some advantages of the PY GCMS method? Well, there are no solvents required. On top of this, the analysis time is not only much shorter, but we use even less sample volume. A huge bonus to the PY GCMS is this method was actually validated in agreement with the IEC 62321 Part 8 Accord. Let's talk about the analysis of phthalate esters using PY GCMS. Here we will cover how this PY screener allows for easier sample prep and uniform analysis of phthalate ester samples. The PY screener uses phthalate ester polymer standards for PY GCMS. These polymer standards can be prepared very easily without the use of organic solvent. These resin standards are in ribbon shaped in a uniform thickness. As a result, we can prepare samples by just using 2 punches from Frontier's provided sampling toolkit to give us the exact or near exact value of 0.5 milligrams, as you can see in the table below. As for the analysis, we are doing a simple hard-cut EGA with multiple temperature ramps, and the GCMS was set to perform both simultaneous scan and sim, giving us an overall runtime just shy of 20 minutes. Here we can see the mass chromatograms for the phthalate esters obtained by the measuring of our 100 milligram per kilogram phthalate ester standard sample. These were detected with sufficient sensitivity, even at a concentration of 1/10 of the prescribed or required concentration of the regulation. What we can see in the table below is the repeatability as well as the MDL calculated after measuring the 100 milligram per kilogram phthalate ester standard sample 7 times. The repeatability here for quantitative values obtained ranges from 4.1 to 5.7%, and the MDL was around 12.3 milligrams per kilogram up to 16.3 milligrams per kilogram, which are quite favorable results in regards to how low we can actually see. So in our previous slide, we covered our 100 milligram per kilogram standard that contains the phthalates. But in this slide, we're actually going to talk about a separately sold phthalate ester standard, a phthalate ester certified standard, CRIS CRM 11303-006. So for this experiment, what we did was we ran our 1,000 milligram per kilogram or 1,000 ppm phthalate ester resin standard sample to create our 1-point calibration curve. We then ran this CRIS CRM standard as a comparison to see what the quantified values or return or recovery values of the CRM standard was. Looking at both the 1,000 milligram per kilogram standard and our CRIS standard, we were able to determine the yield of these certified values ranging anywhere from 92, 93% up to 109%. So in fact, we were able to prove that using our 1,000 ppm phthalate ester resin standard sample is extremely useful in creating a calibration and doing a semi-quantitation for real-world samples by comparing it to this CRIS CRM certified values. Taking this analysis even further, we now can see a real-world sample as the PVC cable. So we ran this PVC cable against our calibration curve, and we're attempting to measure certain phthalates that were present in this natural sample. In fact, we were able to not only detect but quantify 4 phthalates: DBP, DEHP, which is known as a very popular plasticizer, DINP, and DIDP. And as you can tell, we were able to quantify or semi-quant 4 of these phthalate esters extremely well. In fact, 3 of them, DEHP, DINP, and DIDP, all returned well over the limit based off the Rose restriction values of 1,000 ppm. So DEHP finished at 2,500 ppm, DINP was 4,200 ppm, and then DIDP came in a whopping 1,38973 milligrams per kilogram. So, in conclusion, the PY screener was effective at semi-quantifying the 4 phthalates shown here. We also decided to run a PBT resin, and we were using this as another testing sample to measure or detect any concentrations of DBP, DEHP, DINP, and DIDP. What it turned out with this PBT resin is we did actually detect a phthalate, DEHP, but it was well below the legal limit or the required or restricted limit set upon by Rose as the 1,000 ppm. However, what we did measure and did quantify was this deca-BDE. What is this deca-BDE? Well, it turns out this deca-BDE is a flame retardant, which, funny enough, is also on the Rose restricted list. And we'll talk about that here in the next slide. Brominated flame retardants. I bet you didn't notice that on the previous slide, as it was just above the phthalates. And as we can see here, there are actually 2 types of brominated flame retardants on the Rose restriction list. So we have our polybrominated diphenyl ethers, as well as our PBBs, or polybrominated biphenyls. Both of these brominated flame retardants are used to slow down the combustion process. So they release certain chemicals that inhibit the combustion process. These are mostly used in consumer electronics in order to protect certain plastic components from catching fire. Now, along with the phthalate esters, there are some environmental and safety concerns. Brominated flame retardants are also persistent and toxic to both humans and the environment, and have been shown to cause neurobehavioral effects as well as endocrine disruption. So it is important not only to detect phthalates, according to Rose compliance, but also these brominated flame retardants. So we're about to take a look at an application now where we are using the exact same setup to quantify brominated flame retardant. Using the exact same analytical conditions as the phthalate esters, we were able to quantify or detect a brominated flame retardant. So what we ran here was a polystyrene, and we spiked it with BPBPE, which is a brominated flame retardant. And using the same exact conditions, using our scan and sim mass spec method, we were able to detect this and have the ability to quantify any of the brominated flame retardants using the exact same analytical conditions as the PY screener, making it your one-stop shop for RoHS compliance. PYGCMS in forensics? Really? Well, what we'll see here is there's actually quite a few applications that work with PYGCMS and actually have some pretty important significance as well. Whether it's a crime lab or arson or gunshot residue, we see that forensics often relies on PYGCMS for certain types of analyses. Let's take a look. So what we noticed on the previous slide was a picture of ink. Well, ink variation is actually quite significant in the field of forensics. The information from the forensics examination of inks and paper can be critical to investigations involving things like financial crimes, counterfeiting, terrorism, and anonymous letters used for threatening correspondences, ransom notes, and even kidnappings. For example, as you can see here, the Martha Stewart conviction partially relied on an ink source comparison evidence regarding a suspected stock worksheet alteration. As of right now, thin layer chromatography is the most widely used technique for ballpoint ink examinations. But what we're here to talk about is how we can actually use PYGCMS analysis to determine the differences in ink variation. And so what we did in this application was we took the pyrograms of 35 different ink samples where we created a library. Ink was scribed into a piece of paper and the sample was then pyrolyzed. A random ink was selected, or a random ink from our set of knowns was selected as an unknown to test the viability of this library matching result. So out of these 35 ink samples, we picked one unknown that was actually known to us and ran it against our library. What we were then able to find is actually how viable this library matching is to determine the ink variation. So if we take a look at the results, we can see two figures. Figure 1 on the left shows the pyrograms of the oil-based black point pen inks. So our pyrograms of the unknown, which is actually our known, and 4 inks stored in the library are shown in that figure to the left. The major components of each ink are solvents such as phenoxyethanol and diethylaniline. All of these kind of elute before our 7 minutes of the pyrogram. Inks A through D showed similar pyrograms. However, these small peaks are observed after the 7 minutes. These are dyes and additives and differ from ink to ink. It's difficult to differentiate these inks using only this library matching mass spectrum method because of the certain presence of these ions, 77, 94, and 138, which are from the phenoxyethanol. Thus, a second matching was necessary for the components eluting after the 7 minutes. Now we can see that there's a significant difference in the match quality observed based off the unknown inks and our ink A, B, C, D. So basing off our components after the 7 minute mark, we were actually able to match at a much higher rate and prove that our unknown was actually ink C. PYGCMS of polymeric materials in all forms can routinely be performed with little to no sample pretreatment whatsoever, and this often provides unique information about the composition of the sample. This key fact is what makes it such an extremely useful tool for polymer characterization. And what we've seen so far is that there is no limit to polymer characterization. In this case, when we begin to talk about consumer products, we will go down the lines of mural paint, and even makeup. In this application, we cover eyeliner, and this is used as an example of a complex material because it contains a wide boiling point range of constituents, things like volatiles all the way up to polymers. Being able to use an analysis like EGA and follow that up with thermal zone, facilitating the complete characterization of all of the organic constituents in the sample. What this application also offers is a first look at certain accessories or multiple accessories needed for a wider range of analysis, in this case using a selective sampler, or even the MJT or the microjet trap offered by Frontier. What we'll see is this complex sample requires a unique setup, but leads to interesting results. Let's first take a look at the EGA-MS of eyeliner. And what this shows clearly in the figure to the left is multiple zones or a variety of compounds ranging from low boiling to high boiling compounds. If we take a look at the individual zones in the top portion of the figure, we can see the volatiles constituents like solvents and additives through zones A, B, and C. And then we start to get into our polymers in zones D and E. However, in EGA-MS, we're not really using a normal separatory column. Therefore, a peak that we see in the EGA thermogram often represents multiple compounds. This is clearly shown here in the bottom portion of the image, or our two-dimensional multi-ion chromatogram, which uses the 2D display feature of F-search. For example, just taking a look at the peaks observed in zone A seem to be essentially the same in peak shape and apex temperature. In this case, we can see that the main component in zone A can be identified as 1,3-butane-diol. On the other hand, zone B, we see that multiple volatile compounds are easily observed. In a case like this, identification cannot be done purely using EGA alone. Each zone must then be analyzed independently using Hart-Cut EGA GCMS. Here we can see the results of our Hart-Cut EGA GCMS run. What you'll notice in the figure to the right is zone A, B, C, D, E are now all broken down, but now using a separatory column. And what this gives us the ability to do is to take a deeper look into each of those thermal zones. For example, zone A contains 1,3-butane-diol, as well as a number of other volatiles, while in zones B and C, some relatively high boiling compounds derived from additives are observed. Moving down to zone D, we can see MMA, or methyl methacrylate, as a pyrolysate of the polymer. This is the monomer, of PMMA, which is a polymer commonly used in paints and is formed by the pyrolysis of PMMA. In our final market of the day, we break down our material testing market and how PY-GCMS fits into this market. Now, material testing is extremely vague and can cover a large range of materials, but what we're actually going to focus on is quite a unique application and offers an even more unique PY-GCMS configuration. If you were thinking solar panels from the previous slide, then you were absolutely correct. And that's exactly what we're going to talk about in our final application of the day. Materials that are used in solar panels are expected to maintain such a high level of performance for over decades, despite the harsh environmental conditions like high temperatures and UV light to which they are subjected to outdoors. However, there is a growing concern that UV-induced degradation may occur in materials that are used in modules such as ethylene vinyl acetate, or EVA, which is a copolymer used as a clear encapsulation film. What we're going to talk about in this application is how we subject this EVA film to a UV light and also utilize PY-GCMS. In order to test or simulate environmental conditions that a solar cell may face, we need some sort of configuration that would not only give us the ability to expose it to UV light, but also higher temperatures. And with the UV irradiation or UV irradiator from Frontier, we get exactly that. Here we have the ability to expose a sample to certain levels of UV light for an extended period of time, while also subjecting it to furnace temperatures that we would typically see in a pyrolysis unit that are more consistent with environmental conditions. And what we actually take a look at here, and we'll go into the results in a second, but what we actually take a look at here is subjecting certain solar materials or the EVA film to different levels of irradiation time. We also can change the atmospheric conditions here where we expose it to an air-like environment rather than an inert gas like helium. And we'll see how these different irradiation times can actually affect the results and show the breakdown of EVA film. In the first experiment, we subjected samples of EVA copolymer to different levels of irradiation. What we can see here is actually a comparison between the two via an irradiation time of 0 hours or an irradiation time of 1 hour. And what you will automatically notice is even after 1 hour, we are seeing much more degradation and breakdown within that first 5 minutes of the run. With 0 hours of irradiation time, we are seeing compounds like CO2, acetone, cyclosiloxane, so like D3, D4, D7, D8. However, just by bumping up that irradiation time 1 hour, we are now saying CO2, formaldehyde and propylene, acetaldehyde, butene, acetone, isopropyl alcohol, butanol, and acetic acid. We also are seeing an unknown kind of pop up after that irradiation. So just after 1 hour of irradiation, we're seeing quite the breakdown and degradation of this EVA copolymer. We didn't think stopping at 1 hour was enough, so we subjected the sample to not only 2, but then 5 hours of UV irradiation. And as we can see, the comparison between even the 1 hour and the 2 hour are a huge increase in our CO2, formaldehyde, propylene, acetaldehyde, acetone, all of those. So increased degradation as well. Jumping into the 5 hour now, we are seeing a whole new realm of components past 5 minutes. So we have our octadiene, diacetylethanine, our D4 plus decene, the undecadiene and dodecadiene, as well as an increased response of our unknown. So just basically sampling those or exposing those to different hours of irradiation, up to 5 hours of irradiation here, show massive degradation in the EVA copolymer. With that, I hope you enjoyed our time together. I hope you learned a little bit today about all the different applications, as well as some of the more niche applications like this one here. But I do hope you will take something home with you. Again, all of these application notes are available for download in the additional resources section. If you have any questions, please submit those, and we'll look forward to getting those answers back to you as soon as we can. And with that, I'll go ahead and pass it back over to Nicole.
Wow. Thanks for showing us those applications, Alan. The possibilities seem endless with this sample introduction technique. We look forward to hearing from you next time in our panel discussion for sure. Well, it looks like we won't have time for questions today, but for those who have asked, we will be contacting you directly. Also, for those that asked about techniques, use cases, and method questions, please be sure to check out our next PY webinar. We have an expert panel answering your questions live. And if you hadn't had a chance to check out the resources, don't forget to take a look. We have some upcoming pyrolysis talks and posters you won't want to miss. Again, I want to thank everyone who attended and our speaker, Alan, and we look forward to seeing you all in our next webinar where you can talk to the pyrolysis experts live. Have a great day, everyone.